Hi all, welcome to new class. Today's class is the continuation of stability analysis, and the first method to go for stability is Routh Hurwitz Criterion. The closed loop transfer function of a system. Closed loop transfer function of a system is the ratio of two polynomials, that is, there will be numerator and denominator, and the denominator polynomial of the closed loop transfer function is called the characteristic equation of the system. And the roots, so the roots of the characteristic equation of a stable system should lie on the left half of S plane. So the roots of this characteristic equation should lie on the left half of S plane for a system to be stable. So for a system to be stable, the roots of a characteristic equation should lie on the left half of the S plane. So the root should have negative real parts. And the Routh Hurwitz criterion is an analytical procedure for determining whether all the roots of a polynomial have negative real parts or not. The first step in analyzing the stability of a system is to examine its characteristic equation. And the necessary condition for stability is that all the coefficients of the polynomial be positive. If some of the coefficients are 0 or negative, it can be concluded that the system is not stable. The Routh stability criterion is based on ordering the coefficients of the characteristic equation. That is, this is, let a0 s raised to n plus a1 s raised to n minus 1 plus a2 s raised to n minus 2 plus etc. plus an minus 1 s plus an equal to 0, where a0 is greater than 0. So Routh stability criterion is based on ordering the coefficients of the characteristic equation into a schedule called the Routh array. Routh array. So Routh array means it is like s raised to n. Here the coefficients are a0, a2, that is, first one is a0, next is a0 means the highest power of s, the coefficient of highest power of s. Next is a2, then a4, a6, a8, like that. Next s raised to n minus 1, and it is like this, that is the second one, a1, then a3, a5, a7, a9, etc. Then s raised to n minus 2 is b0, b1, b2, b3, b4, etc. Then s raised to n minus 3 is c0, c1, c2, c3, c4, etc. Then etc. s raised to 1 is g0, s raised to 0 is h0, like that. So here we have to find b0, b1, b2, then z0, z1, etc. So this is the Routh array. So the characteristic equation we have to write in this manner, that is in the Routh array. And The Routh stability criterion can be stated as the necessary and sufficient condition for stability is that all of the elements in the first column of the Routh array be positive. If this condition is not met, the system is unstable and the number of sign changes in the elements of the first column of the Routh array corresponds to the number of roots of the characteristic equation in the right half of the S-plane. And if the order of the sign of first column elements is like plus, that is positive, then minus, then positive, then here plus 2 minus is considered as one sign change and minus 2 plus as another sign change. So if this is the case, then this is plus 2 minus 1 sign change, then minus 2 plus another sign change. So there will be 2 roots in the right half of S-plane. In this case, there will be 2 roots in the right half of S-plane. So if all the column elements are positive, then it will be stable, and if any one is negative, that means the system is unstable, and the number of sign changes determines the number of roots which lie on the right half of S-plane. And here, if n is even, then s raised to n row is formed by coefficients of even order terms, and s raised to n minus 1 row is formed by coefficients of odd order terms. Also, if n is odd, then s raised to n is formed by the coefficients of odd order terms, and s raised to n minus 1 row is formed by coefficients of even order terms. The other rows of the Routh array up to s raised to 0 can be formed by the following procedure. That is, each row of the Routh array is constructed using the elements of the previous 2 rows. That is, this row is constructed using the elements of these 2 rows, and this row is constructed using the elements of these 2 rows, like that. So consider the 2 consecutive rows of Routh array as this, that is, s raised to n minus x is x0, x1, x2, etc. Then s raised to n minus x minus 1 is y0, y1, y2, etc. The next row is s raised to n minus x minus 2, that is z0, z1, z2, etc. Then the elements of s raised to n minus x minus 2 is, that is z0, z1, z2 are, z0 is minus 1 determinant of the elements of previous row, that is x0, x1, y0, y1, that is x0, x1, y0, y1 divided by y0, and that is equal to y0 into x1 minus x0 into y1 divided by y0. That is, z0 is multiply these two minus these two divided by this one. So like z1 is z1 equal to minus 1 into determinant of x0, y0, that is x0, y0. The next elements are x2, y2. x2 y2 divided by y0, and that is y0 x2 minus y2 x0 divided by y0. Then z2 is, if there is x3 then y3, then z2 is minus 1 determinant of x0 y0, then x3 y3 divided by y0, and that is y0 x3 minus x0 y3 divided by y0. So like this we have to construct the Routh array, and we have to find the elements of the Routh array. And here the elements z0, z1, z2 are computed until an element equal to 0 or for all possible computations are as shown like this. And in the process of constructing Routh array, the missing terms are considered as zeros. If there is a missing term, then it is considered as 0. Also, all the elements of any row can be multiplied or divided by a positive constant to simplify the computational work. In the construction of Routh array, one may come across the following three cases. Case 1 is normal Routh array, that is non-zero elements in the first column of Routh array. Then case 2, a row of all zeros. Case 3, first element of a row is 0, but some or other elements are not 0. So in the case 1 is the normal Routh array. That is, here the Routh array can be constructed as explained before. Here the sign changes are noted to find the number of roots lying on the right half of S plane, and the stability of the system can be estimated. That is, if there is no sign change, then in the first column of the Routh array, then the system is stable. That is, all the roots lying on the left half of S plane and the system is stable. And if there is sign changes, then the system is unstable, and the number of roots lying on the right half of S plane is equal to the number of sign changes, and the remaining roots are lying on the left half of S plane. And case 2 is a row of all zeros. So an all zero row indicates the existence of even polynomial or auxiliary polynomial, and the coefficients of the auxiliary polynomial will always be the elements of the row directly above the row of zeros in the array. That is, if s raised to 4 is like 1, 2, 4, 7, then s raised to 3 is 0, 0, 0. So here the row above s raised to 3, that is s raised to 4, represents the coefficients of the auxiliary polynomial. And by solving this auxiliary polynomial, we get the roots. That is, the roots can be purely imaginary or real or complex. The roots of an even polynomial occur in pairs that are equal in magnitude and opposite in sign. So these roots can be purely imaginary, real or complex. and the purely imaginary and purely real roots occur in pairs. The complex root occur in groups of 4, and the complex roots have quadrantal symmetry. So purely imaginary and real be like this. This is real roots, and complex roots are group of 4 like this. There are two methods to analyze this case too. So in the first method, determine the auxiliary polynomial a of s. Then second one, differentiate a of s with respect to s, that is d by ds of a of s we have to find. Then the row of zeros is replaced with the coefficients of this d by ds of a of s. Then solve the Routh array. So while solving, if there is sign changes in the first column of the Routh array, then the system is unstable, and the number of roots lying on the right half of S plane is equal to the number of sign changes. And if there are no sign changes in the first column, then Routh array, then all the zeros row indicate the existence of purely imaginary roots, and the system is limitedly or marginally stable. Limitedly or marginally stable. So limitedly or marginally stable means if there is no sign changes in the first column of Routh array, then all the zero rows, that is all the zeros row indicate the existence of purely imaginary roots, and the roots of auxiliary equation lies on the imaginary axis, and the remaining roots lie on the left half of S plane. In the second method, determine the auxiliary polynomial a of s, then divide the characteristic equation by auxiliary polynomial a of s, then construct the Routh array using the coefficients of quotient polynomial. Next is the case 3, that is first element of a row is 0. First element is 0, but some or other elements are not 0. So in this case, if a 0 is encountered as first element of a row, then all the elements of the next row will be infinite. To overcome this problem, let 0 be equal to epsilon, and complete the construction of array in the usual way. That is, construct Routh array with this epsilon, then finally change this epsilon to 0 and determine the values of the elements of the Routh array which are functions of epsilon. So these are the 3 cases while constructing the Routh array. So this is about the procedure for constructing the Routh array. So in the next class, we will discuss about the problems related to Routh array, that is to find the stability of a system and how we can use this Routh array to find the stability of the system. So thank you for watching the class. If you like the classes, please like, share and subscribe my channel.